And then, yeah, we can have questions after the exercises. Please remember to unmute you when you start showing your lecture.
Yeah. Can you see my screen? All right, so I'll introduce the first exercise in this series. So for the first exercise, we are looking at calculating the excited state of formaldehyde using the UAME model. So we start with closed shell reference state, and then using our excitation operator, we calculate our excited state for formaldehyde. Looking at the left side here, I have my orbitals, the HOMO and the LUMO orbitals of formaldehyde represented here, and B1 and B2 are their symmetries. And UAME is a particularly interesting method because it allows accurate description of excited state, and more importantly, it helps to conserve the number of alpha and beta electrons. I'll quickly go on to how to set up this calculation in IQ mode. So the input file that we are using for this exercise is formaldehyde.xyz. You should be able to import this into IQ mode, and then please make sure that when you're setting up the calculation, your charge is set to 0 and your multiplicity is 1, because formaldehyde is a neutral molecule and the ground state is singlet. If you import this input file correctly, you should see this in your RAM section. So let me go through a few of the keywords just to make sure that you understand what you're doing. So EE singlet here helps you to request for number of excited state that you want. So formaldehyde belongs to the C2V point group. So in here, we are requesting one excited state for each of the E reps. E triplet help you to request for triplet state in the same way as the singlet state. And the mem total help you to request for the total memory for the calculation. I believe that in this exercise, you have 4,000, but based on what the information that we have from the Q-Chem team, you have to use 1,000 for this calculation. And the CC transprobe is, you have to turn this on to request for transition properties. And just for future references, in order to generate NTOs, you have to set the number of NTOs pair that you want, and also make sure to turn on state analysis. But for this exercise, you wouldn't be able to visualize the NTOs IQ mode. So just for future references, please make sure to turn this on when you want to analyze NTOs. All right, I believe this is all for this exercise, so I'll let the next person introduce the next exercise.
Okay, right. We'll stop sharing. And, yeah. Remember, unmute yourself.
Yes, in this exercise, you'll be calculating the core ionization energies and core excitation energies for the formaldehyde molecule. Here are the images of what exactly you'll be calculating. XPS is ionization, XA is EE, and XPS is IP. So the formulation is very similar to simple valence excitation and valence ionization, but there is a trick involved, which is called core valence separation. So this trick requires certain core orbitals to be frozen. So you have to be careful in setting up this calculation. So what you will do is you'll import the formaldehyde.xyz to IQ mode, and this keyword is used to freeze certain core orbitals. So the example shown here calculates the core ionization energies, the carbon edge core ionization energy. So the end-frozen core needs to be set to 2. So if you want to calculate the oxygen edge core ionization energy, you have to change it to 1 using IQ mode. The other keywords you have encountered before, for ionization energies, it's important to set CC to Dyson if you want to see the Dyson orbitals. And for excitation energies, you have to comment it out. And if you want to calculate the excitation energies, you should remove the CVS IP states and include CVS EE states. And yeah, that's all for this exercise. Stop.
All right. Hello, everyone. So for the equational motion spin flip exercise, we're going to use the UMSF method to calculate the singlet and triplet excited states in methylene. So I just want to recap a few of the things that Professor Krylov said during her presentation, is that the UMSF is an extremely powerful tool to compute on within a single reference framework, both closed shell and diradical states in molecules. So that's exactly what we're going to do for methylene. We have our reference state, which we choose to be a triplet states, and we can get both closed shell and diradical species, which are fairly common in many molecules and also in chemical reactions whenever we have bond breaking. So let's take a closer look to the exercise itself. It's very, very simple, straightforward, and fast. So you need to download the methylene structure from the drive. And once you load it in IQMol, you just need to change the multiplicity so that we want to start from a reference that has a triplet state. And these are all the keywords that you need in order to run the calculations. So we are invoking a spin flip with the spin flip states keyword. Don't worry too much about the symmetry. We're going to discuss it in the breakout room. But it is important that you set up these two keywords, as we need to make sure that we can distinguish among the excited states that we calculated which ones are singlet and which one are triplet states, or if we have spin contaminated states. Once excited states are calculated, we just need to calculate the energy gap, and that's it.
The example for EOM electron attachment and EOM double electron attachment methods. EOM-EA and DEA describe target states by electron attaching operators. When using cluster reference, target states are naturally spin pure. EOM-EA is good for certain doubled states, like the sodium atom, in the ground and excited states, while EOM-DEA can describe diradicals, for example, methylene, as well as bond breaking. State and transition properties can be computed for both methods. The example for EOM electron attachment is magnesium hydroxide. The alkali earth atoms like magnesium have two valence electrons in the electronic configuration. They form ionic bonds with hydrogen-like ligands, and for example, the OH group, yielding doublet radicals with an unpaired electron localized on the metal. EOM-EA can describe both ground and excited states. A Dyson orbital is a great tool for showing where this unpaired electron goes. To set up this example, please import the magnesium OH structure to IQMol, and remember to use the cationic reference in the molecule section, as the target states will be generated by attaching one electron to it. Compute 3 target states as listed in the EA states section. In this RAM section, the bottom part under the Dyson orbital shows how to set up the calculation in a way that will calculate the Dyson orbitals, which can be viewed in IQMol. And the example for EOM-DEA is magnesium, 2 magnesium atoms separated by the acetylene linker. MgCCMG is a diradical, has 2 unpaired electrons. It's best described by EOM double electron attachment method. To set up this example, import the MgCCMG structure to IQMol. And in this case, remember to set up the charge to +2. DEA states have DEA singlets and triplets way of including separately as the keywords to start these calculations. Again, we'll be computing 2 states in both singlets, 3 target states in both singlets and in triplets. Request transition properties between the EOM states. The keyword is CC transprop equals to 2. And the reason why this is to 2 is to account for transitions between the target states, which will be the ones that are important for describing the neutral molecule. And this is in contrast to the CC transport property is equal to 1, where the transitions are calculated between the reference state and the EM states. And you have to avoid that in this calculation, where the neutral molecule, both ground and excited states are described by the EM states. And that's it for this example.
Excellent. So let's go and do these exercises, and then there will be Q&A. So I hope the transition to this breakdown rooms is working, and yeah, good luck with the exercises.
Yeah. Great. Thank you all so much for that. Yes, so I will stop the recording now and put everyone into their breakout rooms.